So welcome students. In today's class we will study about the fluidization. So in last class we have studied about the flow through the fixed bed. So this is the next topic of the same chapter. So in the fluidization, to understand the fluidization, let's observe these pictures. So here suppose this is a fixed bed as we explained in the last class. Here this is the length of the fixed bed or height of the fixed bed, which is the HM, and the gas or liquid is flowing from the bottom to the top. Okay, so what's happened when the gas flows from, or the gas or any fluid, gas or liquid will flows from the bottom to the top, that the fluid will exerted the force on the particles present in the bed. Okay, and the opposite force will be the gravity due to the mass of the particles. So when the velocity of fluid is low, at that time what's happened, the gas will pass through this bed slowly and there is a pressure drop across the bed. Okay, and due to the higher force, because the gravity is higher than the buoyancy force, the particle will not move upward direction, it will stay in the bed. Okay, now suppose you start to increase the force, start to increase the velocity. Then what's happened, when you start to increase the velocity, then the force, buoyancy force will also increases. Okay, and it will slowly then it will you will get a point where the buoyancy force will overcome the gravity force of the bed, gravity of the mass of the particles. So when when it happens, when the buoyancy force is equal to the gravity force, at that time you will find that the height of that bed will slightly increase at the same point. Okay, and the porosity or the void fraction will also increase because height is increased. So that point is called the minimum fluidization velocity. Okay, so this is the point where the buoyancy start to overcome the gravity. So at that the point we call the velocity is called the minimum fluidization velocity, and the pressure drop across the bed is called the minimum fluidization pressure drop, or the fluidization pressure, required fluidization pressure. Okay, so what's happened when you, if you plot the velocity versus the velocity versus the pressure drop. So suppose we here we plot the superficial velocity of gas versus the pressure drop. Superficial velocity is the velocity of fluid when we assume that the column is empty. Okay, so same velocity can be represented by the superficial velocity. So it is the similar to the same actual velocity. So when you plot the superficial velocity of gas versus the pressure drop across the column, so when the bed is fixed, when the gravity force is high, you will find that when you increase the velocity of fluid, the pressure drop across the column will increase, but the height of the column, this is the height of the column, will remain constant. And at the point when the pressure drop, when the buoyancy force just equal to the gravity force, you will find that the bed slightly moves upward. When both forces are equal, the bed slightly moves upward direction. Okay, so the length of the bed will slightly increase, it will increase from A to B. So that is called the minimum fluidization velocity. So here you got the minimum fluidization velocity, and when you again increase the velocity, then you will find that pressure, then the pressure drop will remain constant and your length of the bed will start to increase. So in this diagram, when after achieving the minimum fluidization velocity, when you increase the velocity of gas or liquid in the column, then particles of the inside the bed or the granules inside the bed start to float, start to bounce due to the buoyancy force of the gas, due to the drag force exerted by the fluid on the solid particles. Okay, so that buoyancy force or that drag force will overcome the gravity in this point. Okay, so there are three different type of fluidization. This is the bubble fluidization, this is the sludging fluidization, and this is the pneumatic fluidization. So there is a slight difference between all these three type of fluidization. In the bubble fluidization, the particles slightly accumulated in between the space, and you have the bubbles of air bubble inside the fluidized bed. In the sludge fluidization, particles are stick together, so you have the slight voids inside the bed. So here the density of bed is lower, here density of bed is again higher, and here you have bubbles also. This is called the sludging. Okay, and in pneumatic transport, you have the homogeneous distribution of the particle across the bed. So simplest formula, I am not going to the detail of this all these three type of fluidization. I am only stick on the pneumatic fluidization. Okay, so pneumatic fluidization is the simplest to understand. So in this course we will only study the pneumatic fluidization. If you want to prepare for the GATE exam or higher studies, you should also study about the bubble fluidization and the sludge fluidization. Okay, so in this course we will stick on the pneumatic fluidization. Okay, so you understand the fluidization. Fluidization is when the buoyancy force of the fluid of the upward direction, the buoyancy force which is act on the upward direction will overcome the gravity force, and and as a result particles start to move upward direction. That is called the fluidization of bed. Okay, so when the fluidization start, then the height of bed is called the minimum fluidization height, that is represented by LMF. And when the fluidization start, at that time the porosity of both, I have already told you, when the both forces are equal, the height of bed is slightly higher, and when the height will change, then the porosity, of course the porosity of bed will also change, so it will be slightly higher. It will represent by the xi-mf. This is the void fraction of porosity of the bed when the fluidization starts. So this is when you have the minimum, you achieve the minimum fluidization velocity, which is represented by v dash mf. This is the superficial minimum fluidization velocity. Okay, so once the fluidization starts, you can correlate the porosity or the void fraction of the bed to the length of the bed by using this formula. This formula is derived by equating the volume of the solid particles, because in the if the tower is closed, in this diagram, if the tower is closed in from the upward direction, or you are in the fluidized zone only, means particle, the buoyancy force is not enough to move the particle, to remove the particle from the tower. So it is suspended only, it is not removed from the particle. It is buoyant, it is moving upward direction, but it is not removed from the particle. It is not a moving bed, it is only the fluidization bed. So in this case, the overall volume of the solid particle will be same. In the different scenario, when you increase the velocity, the fluidization will start, but the overall volume of the solid particle will remain same. So you can correlate the length of the fluidized bed to the porosity by using this formula. Okay, so this is the L1, this is the first condition, this is the second condition. Here the length is L1, here the length is L2. This is the overall solid volume of the particle, this is also overall solid volume of the particle, both will remain same. So you can calculate the length of particle L1 by L2 equal to 1 minus xi2 by 1 minus xi1. So here this is the void fraction or the porosity of the particle of the bed at the two different cases. So from this formula you can calculate the height of the bed. Okay, now the second, the most important parameter in this case is the pressure drop and the minimum fluidization velocity. So what is the minimum fluidization velocity and how much pressure drop occurs at that minimum fluidization velocity? So that, as we discussed before, that at the minimum fluidization velocity, the gravity force and the buoyancy force will equal, है So you can by using that formula you can calculate the minimum pressure drop in the column. So this is the buoyancy force delta P by A. This is the pressure drop per unit area. It will the buoyancy force which work at the upward direction, and this is the gravity force which work as the downward direction. So both are equal in the minimum at the point of minimum fluidization velocity. So you just rearrange this term, you will get delta P by Lm. This is the pressure drop per unit length of the column or per unit height of the column, that is equal to 1 minus xi-mf. This is the porosity at the minimum fluidization velocity. Rho p is the density of particle, rho is the density of fluid, and g is the gravity. So this formula can be used to calculate the pressure drop at the minimum fluidization velocity, SI. This is in the SI unit, this is in the English unit. English unit you have the GC also. Okay, so this formula can be equivalent to the Euler's formula, which we have studied earlier in the last class. In last class we have studied that the impact bed column, the pressure drop equal to delta P by L equal to this value. Okay, so if you have the turbulent flow, then the first term will be neglected. If you have the laminar flow, where the Reynolds number of particle is less than 10, then the second term will be neglected. You have only the first term. If you have the turbulent flow, when the Reynolds number of particle is greater than 1000, then the first term will be neglected. You have only the second term. And if you have the intermediate values of the Reynolds number of particle, means Reynolds number of particle is greater than 10 and less than 1000, then you have the both term. This is called the Euler's equation. So this equation represents the pressure drop inside a packed bed, and this is also a packed bed because at that point the bed is not in the fluidization state. The fluidization is just started. Okay, the both forces are just equivalent, so particles are not start to move. It is only it is in the packed bed state only. Okay, so you can equivalent these two equations. Okay, when you equivalent these two equations, the pressure drop term will be eliminated. Okay, so you have the final equation in this form, equation 3.134. Okay, here Vmf is the minimum fluidization velocity, superficial velocity, rho is the density of fluid, phi s is the sphericity factor or the shape factor, psi mf is the void fraction or the porosity of the bed, mu is the viscosity of fluid. Okay, dp is the equivalent diameter of the particles, then rho is the density of fluid, and then other terms, rho p is the density of particle. Okay, so you can see that these all terms, dp is the equivalent diameter of particle, this is depend upon the particle shape, then xi is the porosity of the fluid or the void fraction, phi s is the sphericity, it will again depend upon the particle, mu and rho depend upon the property of, this is the physical property of fluid, and rho p is the physical property of the particle. So these all are the constant basically. Okay, so you have here you have the variable as a Vmf. So Vmf is the only variable. So if you substitute the all values, you will get the second order algebraic equation. Okay, so here Vmf is square multiplied by a plus Vmf dash square multiplied by a plus b multiplied by Vmf minus c equal to 0. So you have the second order algebraic equation. When you solve this equation, you will get the minimum fluidization velocity. Now this equation can be more simplified for the special case. Suppose your Reynolds number of particle is less than 10. At that point, this first term can be eliminated. You have only these two terms. So in the laminar flow, you have only the linear equation, Vmf equal to a constant value based on the porosity and other properties. And if you have the only the turbulent flow, means Reynolds number is greater than 1000, then this second term can be eliminated, this can be dropped down, you have only first term and third term. In this case, you can easily calculate the velocity of or minimum fluidization velocity. Okay, so this is the simple equation which can be used to calculate the minimum fluidization velocity. Once you know the minimum fluidization velocity, you can substitute the value of minimum fluidization velocity in this equation or in this equation. You can calculate from here only you can calculate the pressure drop. Okay, or you can also calculate the value of the other parameters. Now this is the same equation in terms of Reynolds number. Here just we substitute the dp Vmf rho by mu. It is the Reynolds number of fluid. It is not the Reynolds number of particle. It is the Reynolds number of fluid. Okay, so here we substitute for the Reynolds number of fluid, and this is also the similar type of property. Okay, which we have discussed in the last class. So these equation can be used to calculate the minimum fluidization velocity in case of the transition flow. For the laminar flow you can neglect the first term, for the turbulent flow you can neglect the second term. Now this is a simple example. So here we first calculated the LMF, then once we know the LMF we just substitute the value of LMF and calculate the delta P and the minimum fluidization velocity. Okay, so this is a simple example. You can try this example as a assignment. Now if this is the term expansion, so if you have the laminar flow, then V dash can be represented. I have already told you, that the second term can be first term can be neglected in the Reynolds flow when the Reynolds flow Reynolds number is less than 10, and when you have the laminar flow, so V dash can be calculated by this formula, and these all are the constant. So this can be represented by K1, and V dash is only the function of porosity. Okay. So these are some empirical correlation which can be used when you have the Reynolds number very less than 4 and greater than 1000. These are the empirical correlation which can also be used to calculate the velocity in terms of minimum actual velocity of superficial velocity during the fluidization in terms of minimum fluidization velocity. So this is all about the fluidization in this course. So from in the next in the next class we will study about the measurement of flow of the fluid. Okay, so this the most of the part is already covered in the experiments. Here I have already only covered the derivation parts. You have already done the experiments on the Venturi meter and orifice meter. In this part I will only cover the derivation of the both things and comparison of the both type of equipments. Okay, so now we have only the 2-3 chapter remains, 2-3 topics remain. One is the measurement of the fluid through different type of measuring equipment, then the different type of pumps. Both are covered in the, both will be covered in the this is already covered, the measurement of the fluid is already covered in the experimental part, and the pump will also covered in the experimental part only. So that the question related to this these two topics will only come in the experimental in the quiz related to the experiments. Okay, so in the theory part we will only ask up to the fluidization. Okay, so your theory portion will be covered in the today's class. In the next few classes I will only cover the lab experiment which is remaining in the course.